So far, everything that we've discussed in regards to microscopy has been light microscopy, where we're using visible light or ultraviolet light to illuminate our specimen so that it emits visible light, right? We're working in the visible range. And as we've learned, that has a maximum resolution of about 200 nanometers because the lowest wavelength visible light we can see is approximately 400 nanometers. So sometimes we need to see things that are even smaller. And to do that, we're going to use electron microscopy. So let's have a look at how this works. The first kind of electron microscopy we're going to learn about is transmission electron microscopy, or TEM. So this is a diagram of a typical transmission electron microscope. The person operating the instrument would be sitting, if we can find my pointer, right about here. And let's look more closely at this part of the microscope called the column. And if we look at this little diagram, we can see some important components of the transmission EM. Up at the very top, we've got an electron gun, which consists of an electron source. That's this V-shaped thing right here. And the electron source is usually either tungsten or lanthanum hexaboride. But underneath it, we're going to have a very powerful electromagnet that, when activated, will rip the electrons off of the atoms in the electron source and send them rocketing through the column, where the electrons are focused by a set of condenser lenses onto a specimen, which in this instrument is sitting inside the objective lens. And those electrons are going to interact with components in the specimen. These specimens, like many light microscope methods, are stained with dyes, except these dyes don't impart color to the specimen. They're made of heavy metals. They include things like osmium tetroxide, uranyl acetate, lead citrate, and the osmium, uranium, and the lead will absorb electrons. So the electrons will not pass through the specimen. So there will be some parts of the specimen that are more electron opaque, which will appear darker in the final image. And then there are areas with fewer of these heavy metal atoms that will appear less electron opaque, or they will be electron lucid, and they will appear lighter in the final image. So the electron beam, having now interacted with the specimens, continues downward until it hits a screen down here at the bottom, which in the instrument I used in graduate school quite a bit was covered in some sort of fluorescent substance that emitted visible light in response to being excited by the electron beam. Nowadays, it's often still have a fluorescent screen, but underneath it there will be some sort of digital camera that you can use to actually gather the images. Back in the Stone Ages, when I was in graduate school, we actually had a film camera located right down in here. And I could take like 20 pictures, and then I had to change it out and develop the film in a dark room, and it was really rad and awesome, and it was a good time. But it's also labor intensive, and it's a lot easier just to have the digital images. So, aside from my rambling, why might we want to do this? This is an expensive instrument. My major professor in grad school bought a new transmission electron microscope right before I left school, and it cost nearly $1 million. These are very expensive, so why would we want to use them? Well, let's recall that visible light has a minimum wavelength, the smallest wavelength that we can see. I'll go ahead and use our lambda symbol. There we go. So visible light, lambda of about 400 nanometers, which you will remember gave us a maximum resolution somewhere in the neighborhood of 200 nanometers. But the electron beam that's generated by this electron gun, it has a wavelength of about 0.15 nanometers. That is 2,667 times smaller, which means that our resolution then is going to be 2,600 times better. That's why we do EM. We get better resolution because the beam of electromagnetic radiation that we're using to form the image has a much, much, much smaller wavelength. So let's look at some TEMs and see what kind of images we get. So on the left we have a TEM of the Zika virus, and on the right a TEM of mitochondria. And let's focus on this mitochondrial image a little bit more closely. Look down here at the bottom. You can see a scale bar. So this bar is 50 nanometers wide. So if we look more, I keep saying so, and I need to stop doing it, but I keep doing it. So see, I did it again. I apologize, guys. Look here where I'm illustrating with the pen. You can see the twin railroad tracks of the lipid bilayer. So this width right here is 7.5 nanometers. And we're resolving this just fine. Remember with light microscopy? Whoops. 200 nanometers was the best we could do, 7.5, and we can go further. So we're talking about magnifications not in the range of hundreds to 1,000, but in the tens to even hundreds of thousands of times, and still get good resolution. Because we're looking at such fine details on the inside of a specimen, much like in many forms of light microscopy, these specimens have to be thin section. As a matter of fact, they have to be ultra thin sections. So we're making sections that are just tens of nanometers thick, and that allows the electron beam to be able to pass through the thinner areas, and we get an image like we see here. So the image is very two-dimensional, much like in some forms of light microscopy, and that's because the specimen has essentially been made two-dimensional, which allows us to use this type of microscopy. The other type of electron microscopy that you're going to see quite often throughout this course, and indeed in any career that involves looking at micrographs, is scanning electron microscopy, or SEM. Now this is going to work a bit different because instead of thin sectioning the specimen and passing the electron beam through it, instead the specimen is focused down on, the electron beam is focused on the surface of the specimen down here, and the electron beam is passed over the specimen in this kind of raster pattern over and over and over again. And instead of capturing electrons that pass through or don't pass through the specimen like we did in TEM, we cover the specimen in something that will emit electrons in response to being hit with electrons, in this case gold, and the gold will emit the electrons. We gather them up with a detector and we form an image on the screen. Now, I didn't choose a super high magnification SEM, but you can still see the magnification in this image is 8400x with a 1.19 micrometer scale bar here. So even though this is considered low magnification for an SEM, especially some of the real high-end SEMs that are out there now, it's still 8.5 times greater than you would be able to get with the light microscope. Two kinds of electron microscopy: transmission, in which the electrons pass through the specimen, and scanning, in which electrons are emitted from the specimen in response to being excited by other electrons. TEM, the image is much more two-dimensional, but you can see fine internal structures. In SEM, you can't see the insides, however you do have much greater what we call depth of field, meaning that you can tell that this is closer than this. There's a foreground and a background. That's what we mean when we say depth of field. Keep this in mind as we go through the rest of the course. That's it for now. Study hard. See you later.